Hey guys, welcome back, and today we'll be discussing a simple question called detecting a cycle in a directed graph. So before moving ahead to this question, we have to know what is a directed graph. So basically, it's an edge which is pointing to a particular direction. So for example, if I have vertex A here, the vertex A is pointing to itself. So we call this a self loop, right? And suppose I have another example over here, A and B. So A is pointing to B, B is pointing back to A. So this is a directed graph, and it contains a cycle. Okay, you can clearly see a cycle over A points to B, B points back to A. So we are going in a loop. So wherever we are going in a loop, we can definitely say that we are in a cycle. Okay, my next question to you is that can you detect a cycle in this orange graph? You can pause the video here. Okay, if you have detected it, yes, it's B, C, D, E. So we can start iterating from there. Here we move from A vertex, and we see that we cannot form any particular cycle with A, because A is going to B, B is going to C, and A is directly going to C. So there is no vertex which is actually going back to the A. So hence we cannot form any cycle with A. But can we form any cycle with B? Yes, we can definitely form any cycle with B, because see, B starts here, B goes to C, D, E, and so on. So there is a complete cycle over here. And how many cycle is there in this graph? One. Okay, so in a directed graph, there can be a single cycle and there can be multiple cycle as well. So what is the example for the multiple cycle? Let's look over here. You can look over this yellow graph, and can you tell me the number of cycles which is present over here? You can pause the video here. Okay, I shall begin now. So what you can do, what we have here is that we start with A. A is, there is no vertex which is point. There is a vertex actually which is pointing back to the A, and it is coming from D. So is it possible to actually go to D here? Okay, yeah, there is a path here. We move from. Okay, I will choose a different color pen. So we go from A to B, B to C, C to E, E to D, and then we are back to the A. So there is one cycle here. So what is the next cycle? Let's look over here. So here we have E. E is going to the D. D is going to the F, and F is going back to the E. So there is two cycle here, the pink one and the purple one. The pink is the pink cycle has D, E, and F, and the purple cycle has A, B, C, E, D. So this is a cycle over here. And it's always a good habit to actually write A twice, so that people can understand that yeah, there is a cycle. So D, E, F, and back we are to the B. So this is cycle number one, and we have a cycle number two. So there is one more complicated example. Okay, so can you let's suppose that you might be thinking that we can start with the DFS approach. What we can do over the DFS is that we can choose any vertex, and we can start iterating over that vertex and find if we have already detected an edge or not. Okay, so like if we start with A, we go back to B, and we put in the stack C, and so on. And once we have visited back to the A, we can clearly say that we have a cycle over here. But does it mean that using this algorithm we can always find a cycle? No, the answer is clearly no. Let me tell you why. Because once there may be a case where there is we cannot iterate to the some part of the graph. Let's take for example this graph. Okay, it starts with A. Okay, we go from A to C, C to D, E, and there is a one cycle over here. That's pretty good. But there may exist another cycle, and what is a cycle? You can clearly see it's from G to H. So there is a cycle over here. Now let's imagine if the cycle was not there and it was clearly, and let's say that you have applied a DFS algorithm over here. So we start with A, okay, C, D, E, and F. But there is no way to reach H. Why we cannot reach H? Because there is a no, the arrow over here of H is pointing to F. There is not arrow like this. If it had been like this, we can clearly put H in the stack and traverse this path. But here it's not the case. Hence, we cannot reach over the cycle. And since we cannot reach over the cycle, our answer would return that yes, there is no cycle in the graph. But as we all know that there is a cycle over graph, and it's DH. So what algorithm can we use to make sure that we are able to detect all the cycles? So yes, you're thinking right. We have to check for each and every vertex. For example, A, C, D, E, F, H, and G. So before moving ahead, let me tell you some simple terminology which will be helpful for you. So for example, there is a thing called forward edge and backward edge. So backward edge is required for us because it's help us to determine the cycles in the graph. For example, here, let's see, we start with A, B, C, D, E, and then we move back to the B part. Okay, so this dotted lines denotes that we are moving back to the B. So we suppose we started traversing from A part or B. So since if we detect the edge which is going back to the parent vertex, we can clearly see that that's a back edge. And what is a forward edge? Forward edge is basically any vertex which is pointing to the any vertex which we have not visited. Okay, for example, if we start visiting from here, A, and then we move to B, and since we move from B to C, we can clearly see that A is already pointing to C, but we haven't visited C yet. So forward vertex edge is basically that edge which points to the vertex which we have not visited in an array. Okay, so let's move ahead and discuss what approach can we do. So there may be exist as I explained in my previous example, there can be a multiple cycles, and there is a another thing called cross edge. Cross edge basically means that, okay, we can clearly see that once we start traversing from A, we move to F part. Okay, but there is no way we can actually traverse this part. But if there is an edge which connects the suppose I divide this, okay, and suppose there was no this edge. So would have been possible to actually traverse this whole graph? No, because if we start iterating from A, C, D, E, F, there is no way we can actually reach the edge vertex. So, but if there is an edge which connects these two graphs, we can say that it's a cross edge. Now, how cross edge is different from this pink edge? Because you can see that if F connect edge, we can say that yeah, the graph is in. We can reach that edge vertex. But if we cannot reach, and if a cross edge is basically determined by, if we remove that, it will be basically two different graphs. You can say in simple word. So what will be our approach in this? So we will apply a DFS algorithm for each and every vertex in the graph. So, but here we have to make sure that we have to maintain two stacks. Now, what I mean by that is that in general case, you keep a vertex. I'm sorry, vector. In general case, when you're doing a DFS, you keep a vector bool with you say that visited, and you put all the values to the false. But here we need to make sure that there will be also called a recursion stack. Now the recursion stack is a different stack. What happening here in a recursion stack is that it works the same as a visited stack, but what it does is that suppose if we find a cycle, for example, with start with A, we move to B, and when we move back to A. So in this case, we will mark A as visited. But if let's suppose that if we are doing a normal DFS algorithm, so in this case, A and B both will be visited, and in the next case, we would not be visiting B because it has already been marked visited in a normal visited stack. Hence, we need to maintain another stack which has to which makes sure that every vertex is actually visited, and if in that case we have to make it a false value. Like, just a second. Okay, so what I was telling that in the recursion stack, what happened is that the we are only visiting. Suppose that in a visited one, we mark A as true because we have visited this vertex. That's okay. But when we are going in the cycle, we need to mark all these vertex to be true. For example, if we had some complicated cycle like A, B, C, and we go back to the or maybe to A. So in this case, in the DFS, what will be happening that all these value will be going true, but we do not want this to happen. Hence, we have to update our recursion stack in this case. And recursion stack will be marking B as a true, C as true, and A as true. What will happen is that we have to check the recursion stack. So if the recursion stack return true for A, that means we have detected a cycle. For example, A will be marked as true here, but in the visited one, right? Because we have visited the A node. But what happens is that when we start visiting the all the neighbors of A, which is C, or basically the edge which is point A pointing to B, C, and A, we'll be updating our recursion stack and marking these as true. So in this case, what happened is that we are not actually affecting this visited one, and we can so on visit all the vertex present inside the graph. And after this, we have to mark this as true, true. But once we exit the cycle over here, we have to mark all of them as false. So that's a basic code behind this. And if we encounter any visited vertex in a recursion stack, we have found a cycle. So if we detect another time A, if we have detected A another time, we mark as, and if it is true, that means we are back in the cycle and we have to exit the recursion stack, but we have also make sure that we mark all of them as false. Okay, and that's it, guys. And the time complexity for this algorithm is V plus E, that is vertex plus edge. And you might be the word visited keeps track of all vertex to iterate. So that's a basic code. I will send the code link is in the description. And so thank you guys. If you have any suggestion for me, or if you want me to make a particular video of about a specific topic, you can put your comments in the link. You can put your comments. So thank you guys.